All right, and you know, we'll just go through this quickly. There'll be an equation sheet, just like on the exams. And then you have a periodic table, just like the exam. And most of the questions will be either the same or similar to ones that were on the 5 exams. You need to remember the difference between physical and chemical properties and physical and chemical changes, and what's the easiest way to discern if it's a chemical change instead of a physical one. Do you remember?
Same mixture throughout. Same.
If something undergoes a chemical change, you're making a new substance. A physical change, like an ice cube melting, you're not making a new substance. It's still water. So that's probably the easiest way to kind of distinguish these. The physical properties of materials doesn't involve what other materials you can make out of them. Okay. So it's the physical properties are things like melting point, boiling point, the color, what does it smell like, refractive index, density, whatever. Quite a few things on this study guide. We'll move along. Subatomic particles, obviously, you should recall that the atom is mostly empty space. The more massive particles are in the center of the atom. We call it the nucleus. In the nucleus, there are protons that we say have a +1 charge, neutrons that we say have a 0 charge. And they're held together actually by nuclear binding energy, which is a different force than the other forces we talked about. Then the atom's mostly in empty space, and electrons are in specific quantized energy levels we call orbitals. And electrons, of course, have negative charge, and they're much, much lighter than protons and neutrons. Protons and neutrons have a mass of about 1 atomic mass unit. They're not exactly the same to each other, but they're both about 1 atomic mass unit. An electron's about 1/2000th of that. So most of the mass of the atom is in the nucleus, and the protons and the neutrons. Density of a substance is its mass divided by its volume. For solids and liquids, usually we use grams per milliliter or grams per cubic centimeter as the units. For gases, because they're very thin, we usually use grams per liter. The specific gravity is the density of a substance divided by the density of water. And since the density of water is about 1 gram per milliliter, numerically, the specific gravity of a substance and its density are about the same. I'll give you an example. Aluminum metal has a density of 2.7 grams per milliliter. Aluminum metal has a specific gravity of 2.7 with no units. So the specific gravity is really telling you how many times as dense something is compared to water. So specific gravity doesn't have any units. Now, in the history of chemistry, there was a time that Dalton and others didn't realize that there was actually more than one form of the same element. Later it was discovered that there's more than one form for all the elements we find in nature. If a form of an element is not stable, we say that it's radioactive. But these different forms of the same element, we call them isotopes. So isotopes are different forms of the same element. Obviously they have to have the same number of protons or they wouldn't be the same element. It's the protons that determines what element it is. And that's called the atomic number. So if you have 2 isotopes of an element, what is different about them? The protons are the same. So what is different about different isotopes of the same element?
The neutrons?
Different
They
ones.
have different numbers of neutrons, and they will therefore have different masses. And since they have different numbers of neutrons, they have different mass numbers. The mass number is the number of protons plus neutrons. Now, we talked about significant figures and scientific notation. Are all you comfortable in determining how to write a number in scientific notation?
Can you go over the rule of the zeros and sig figs?
For significant figures?
Yeah.
Okay. One thing about determining the number of significant figures, it's easy for the numbers that aren't, the digits that aren't zero, because they're definitely significant, okay? But zero is the one, the digit that can be ambiguous. So let's look at some examples of that. And if we have a number that has a zero between non-zero entity, it's significant. So for this measurement, this value has 4 significant figures. The zero is significant because it's between non-zero digits. If you have zeros to the left of a decimal fraction, these are not significant. And the reason is they're placeholders. And so for this number, this decimal fraction, it only has 3 significant figures, okay? If you have zeros on the right of a number like this, well, this zero is significant. It wouldn't have been written if it wasn't part of the measurement. There'd be no need to write it. But these are still placeholders. So this measurement has 4 significant figures. And these, again, are placeholders. If you have a number like 1, 2, 3, 0, 0, 0, and there's no decimal point, the zeros are placeholders. Okay? So this has 3 significant figures. And the zeros, you still have to write them. They're placeholders to get the number in the right orientation. These are significant, these are placeholders. But the same number, if you put a decimal point, now these zeros are significant. And this would have 6 significant figures, all of them. Everybody see that? Those are, I guess those are all the possible scenarios of what you might encounter with Z. But, and now it can get tricky. What if these are significant and this is not? You never need to worry about that in this class, but chemists usually put a line under one if all these are significant. And this one's a placeholder. But I don't want you to go there. All right. Everyone comfortable writing numbers in scientific notation?
Mm-hmm.
Everyone know how many significant figures you can have in a calculation if it's a multiplication or division problem?
The smallest.
Whichever measurement has the fewest significant figures, that's the number of significant figures you can have in your answer. Okay. Now, if it's addition or subtraction, you look at the decimal places, and whichever measurement has the fewest decimal places, that's all the decimal places you can report. So the rule's a little different for addition and subtraction compared to multiplication and division. Binary ionic compounds only contain two elements, and so if you have a binary ionic compound, and it's really based on the electronegativities we talked about, metals elements tend to lose electrons, and when they lose negatively charged electrons, they turn into positive cations because they have more protons remaining in the nucleus than electrons in orbitals. So if an atom, a metal atom, loses one or more electrons, it forms a positively charged cation, and think of that letter T, looks like a plus sign. Nonmetals, on the other hand, are more electronegative than metals, generally speaking, and they have affinity for more electrons. And so if a nonmetal atom gains electron, it's going to form a negatively charged anion. Okay? As far as the main group elements, the group number tells for the alkali metals, group 1A, and the alkaline earths, group 2A, and aluminum that's in 3A. The group number actually tells you, one of the things it tells you is the charge of the cation that it forms. So sodium forms an ion with a +1 charge. Calcium forms a cation with a +2 charge. Aluminum forms a cation with a +3 charge. And then for the nonmetals, you have to subtract 8. So chlorine is in group 7A. 7 minus 8 is -1. That's a -1 charge. Oxygen is in group 6A. 6 minus 8 is -2. You can't predict the charge for the transition metals easily, and so you use the formula of the compound to try to determine what it is. Some of the transition metals form more than one cation. And that's what we mean when we say the stock system. When you name an ionic compound using the stock system, in the middle of the name is a Roman numeral that tells the chemist what the charge of the metal cation is. There's a difference between iron 2 chloride and iron 3 chloride. In iron 2 chloride, the iron has a +2 charge. In iron 3 chloride, the iron has a +3 charge. And the formulas that would be different. For iron 2 chloride, since chloride typically it has a -1 charge, in iron 2 chloride, you're going to have 2 chlorides. Don't forget the formula has to add up to a charge of 0. For iron 3 chloride, well, you're going to need 3 chlorides. But don't forget, for iron 3 chloride, the iron has a +3 charge. You're going to need 3 times a -1 or -3 to counterbalance that. Formulas of ionic compounds, the charge, total charge has to add up to 0. But if there's a question, what's the name of an ionic compound using the stock system, you can rule out any name that doesn't have a Roman numeral in it. Just draw a line through it. It's got to have a Roman numeral. And then you got to figure out what the proper Roman numeral is. The molar mass of a compound, if you know the formula of the compound, then you can determine the molar mass by simply adding the atomic masses that are in the formula, okay? And you just use your periodic table. If you don't know the identity of the compound, but you know its mass and its number of moles, that's a very easy calculation. You just take the grams divided by the moles, gives you the molar mass. That would be for a compound if you don't know its formula, but you do know its mass and its moles. So that's a second way of figuring out mole amount. Converting mass to moles, moles to mass using the molar mass. You don't have to memorize those equations, they'll be on the formula sheet. But typically, in converting grams to moles or moles to grams, you need the molar mass of the compound to do that. Balancing chemical equations, we've done that a variety of ways in this semester. Oxidation numbers, I'll have on the exam the rules for oxidation numbers. Chemists assign oxidation numbers that are related to the oxidation state of each element that's in the formula of a compound or a polyatomic ion. And there's rules, generally speaking. If the oxidation number goes up in a chemical reaction for an element, generally that implies there's been an oxidation. If the oxidation number goes down for an element on the left side compared to the right, well then that's where the term reduction came from. It's a reduction, and it corresponds to a reduction in the value of the oxidation number. But again, you can use the rules for oxidation numbers to determine the oxidation number of any element in a compound or polyatomic ion. Types of chemical reactions. How do you know if something's a precipitation reaction? Well, what you look for on the left side of the equation, you have two solutions of compounds, and they'll have aqueous. And on the right, somehow, a solid has formed, or it can have PPT for precipitate. But if you look at the left side of a chemical equation and everything is AQ, which means aqueous or dissolved in water, you mix two solutions, everything's dissolved in water, and then there's a product formed that doesn't dissolve in water and it's a solid or a precipitate, then you know you have a precipitation reaction. Okay? Acid-base neutralization on acids got to have some kind of hydrogen in it, and it reacts with a base to form a salt and water. So acids neutralize bases and vice versa to make a salt and water. And combustion reactions, they're kind of easy to recognize. For our purposes, a combustion reaction is a carbon compound that reacts with oxygen to form CO2 and water. When you burn gasoline, when you burn candle wax, when you burn propane, when you burn butane, when you burn natural gas, all of those are combustion reactions. Those are carbon compounds reacting with oxygen to form carbon dioxide and water. That's what you're looking for. Also, they give off heat. That's why we burn them, because they give off energy. Okay? Dilution of aqueous solutions M1V1 is equal to M2V2. You have to pick one side as the concentrated side, one side is the dilute side. And from a practical standpoint, usually we want to know what volume of a concentrated solution that we already have do we need to make a dilute solution. Okay? So you'll know three of these parameters and you solve for the fourth. A couple of gas laws on the test. Boyle's law, you don't have to memorize it, involves changes in pressure and volume. P1V1 is equal to P2V2. The ideal gas law does not involve changes in any of the parameters involving a gas. The ideal gas law is the interrelationship, mathematically, of the pressure, volume, moles, and temperature. and it's PV equal nRT for pressure. P is pressure, V is volume, N is moles, which is the number of particles, T is the temperature, and R is the gas constant, which will be on the formula sheet for you. What units do you have to have for temperature and using gas laws?
Joules,
What's that?
kilojoules, or
Kelvin.
Kelvins.
Kelvin.
Kelvin. So the temperature has to be in Kelvins, okay? And if the temperature is in Celsius, on your formula sheet will be the simple equation to convert Celsius to Kelvin, okay? Now, yeah, I think most people got this right last time. Can you name some elements that are gases at room temperature and pressure?
Nitrogen,
Nitrogen's in the air right now, yes.
oxygen,
Oxygen better be, or you'll take a permanent nap, okay? Those are two of them.
chlorine,
Chlorine is one. One thing, it says elements that exist as gases. Well, the whole noble gas column. Neon, argon, helium, okay? Also hydrogen is when you have the pure element, is a gas, okay? Good. There's an equation you might have to use. You can determine the quantity of heat energy that's either been absorbed or released by a substance based on its mass, its specific heat, and its change in temperature. And the change in temperature is the final temperature minus the initial temperature, okay? First law of thermodynamics. Well, it's sitting right here. Delta U equals Q plus W. That's a change of an internal energy. And again, sometimes I use capital E instead of capital U for that. But the first law of thermodynamics is really, besides being the change of internal energy of a system is equal to the heat plus the work, it's also qualitatively simply the law of conservation of energy. Energy cannot be created or destroyed. It just changes from one form to another. And so any kind of transformation, you have to be able to account for all the energy. We studied electromagnetic radiation, which has both wave and particle properties. When we talk about electromagnetic radiation as a particle, we call it a photon. It doesn't have any mass, and it's sort of a packet of electromagnetic radiation. But electromagnetic radiation also has wave properties, and we talked about amplitude, wavelength, which is the actual wave, the actual length of one wave cycle. Frequency is how many cycles pass a point in space per second. The velocity of electromagnetic radiation is a constant in vacuum, so it doesn't change. 3.00 times 10 to the 8th meters per second. The energy of a photon, and again, they'll be on the sheet, but those are pretty simple equations. The energy of a photon is Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength, okay? Now, de Broglie discerned and discovered somewhat the fact that and de Broglie also reasoned that if there were particle properties for electromagnetic radiation, in addition to wave properties, well, particles that have mass might also have wave properties in addition to particle properties. And he actually came up with the equation that enables you to determine the wavelength of particles that have mass. But it's only meaningful, it's called the de Broglie wavelength, but it's only really meaningful for very small particles like protons, okay? And they also, the particles have to have mass, of course, a proton has mass. And also its de Broglie wavelength is actually a function of its velocity as well. But suffice it to say that the equation you need to calculate the de Broglie wavelength will be on the formula sheet. And if it's just talking about the concept, the de Broglie wavelength, of course, is the wavelength of a particle that has mass and velocity. The Pauli exclusion principle. These are kind of definition stuff here, aren't they? Pauli exclusion principle was simply that no two electrons in an atom can have exactly the same 4 quantum numbers. At least one of them has to be different, okay? Hund's rule involves what chemists refer to as degenerate orbitals. When you have orbitals like p orbitals, where you have more than one orbital that has the same energy, when you're assigning electrons to those orbitals, by Hund's rule, you have to put one electron in each of those orbitals before you can pair them. And also, the electron you put in each of those orbitals has the same spin. And then the next electron will go and be paired with a previous one if you need to do that. So when you're determining the electron configuration of an atom or an ion, and you're using the Aufbau principle, the building up Aufbau principle, to assign electrons to orbitals, when you get to orbitals of the same energy, like p orbitals, you put one electron in each orbital first, and then if you have more electrons, then you can pair them. And that's simply just repelling each other. Electrons have negative charge, so if you have 3 orbitals available that have the same energy, you're going to put one electron in each first before you pair in one of those orbitals. The Heisenberg absurdity principle, this is like definition type stuff, but you simply, it was mathematically derived by Heisenberg. It's not a statement on equipment and the limitations of equipment at all. It's the mathematically derived principle that it's impossible to know the position and velocity of small particles like electrons. So they're intrinsically probabilistic. Okay? The Aufbau principle just means building up. And when you determine electron configuration, you work from the bottom up. And you can't have any more than 2 electrons in an orbital, as we've seen in the past. We talked about the 4 quantum numbers. There'll probably be a variety of, in addition to the formula sheet, there'll be a lot of the handouts that we had before. There should be information on these 4 quantum numbers. Electron configuration of atoms and monatomic ions. Now, determining the number of valence electrons for the representative elements, which are in groups 1A through 8A, is very easy, isn't it? Essentially, the number of valence electrons is the same as the group number. So if you have an element like sodium in group 1A, you know it has 1 valence electron. If you have an element like magnesium in group 2A, you know it has 2 valence electrons. Aluminum in 3A has 3 valence electrons. Fluorine in group 7A, 7 valence electrons. Okay? So if you have your periodic table handy, and there'll be a periodic table on the test, it's easy to determine the number of valence electrons for the main group elements. Trends in the first ionization energy, and the most important trends in the ionization energy. Ionization energy is the voltage required to ionize an element that's in the gaseous state. And the trend is such, in fact, it's almost predictable. The elements that require the most voltage to ionize are the noble gases. The elements that require the least voltage to ionize are the alkali metals, like potassium and sodium. They actually want to lose some electrons, so to speak. Okay, so those are the two principal trends. Ionic compounds are metal cations and nonmetal anions. A metal atom loses one or more electrons to form a positively charged cation. Nonmetal atom gains one or more electrons to form negatively charged anion. Ionic compounds are held together by these opposite charges of cations and anions, and the ionic bond is a field. Okay? Covalent bonds are formed between nonmetals, and we call those covalent compounds or molecular compounds. And the nonmetals are on the far right of the periodic table, so if there's a carbon and an oxygen in a compound, you know it's a covalent compound. Neither of those are metals. Formal charge, again, a formal charge is entirely different than oxidation number. And you'll have the rules for oxidation number on the test for you. And you'll have the equation for determining formal charge also. As before, the only molecules you really need to be concerned with as involving molecular geometry using valence shell electron pair repulsion theory are methane, ammonia, and water. Obviously, this theory is used for thousands of molecules and ions. Those are only three you need to be comfortable with. Valence bond theory, hybridization of carbon, sp3, sp2, and sp. Whenever a carbon has 4 single bonds, it's sp3 hybridized. Whenever a carbon has a double bond and 2 single bonds, it's sp2 hybridized. Whenever a carbon has a triple bond and a single bond, it's sp hybridized. And based on these hybridizations, sp3 carbon is going to have 4 sigma bonds. An sp2 carbon is going to have 3 sigma bonds and a pi bond. And then an sp hybridized carbon is going to have a sigma bond, 2 sigma bonds, and 2 pi bonds. If you have an entire molecule, and you're talking about sigma and pi bonds, okay, in this molecule it has a double bond, a triple bond, and the rest are all single bonds. Well, the number of sigma bonds, don't forget a triple bond has 1 sigma and 2 pi. A double bond has 1 sigma and 1 pi. So let's do the pi's first. None of the single bonds have pi bonds. So there's 2 here and 1 here, and that adds up to 3. And then there's 1 sigma bond here and 1 here, and then all the others. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for this molecule, there's 10 sigma bonds and 3 pi bonds. Okay? Everybody see how we did that? Microorbital theory, your favorite. Well, I'll probably have the encyclopedia of handouts attached to the final also that you saw before. And we're going to go over the 5th exam here in a second. But yeah, you need to know the equation for bond order will also be on the formula sheet. Very easy equation. The number of molecular orbitals formed is always equal to the number of atomic orbitals that combined to form them. A molecular orbital can accommodate up to 2 electrons, and this was also true with atomic orbitals. When electrons are added to orbitals of the same energy, the most stable arrangement is predicted by Hund's rule. So we use Hund's rule with molecular orbitals, just like we used Hund's rule for atomic orbitals. Low energy molecular orbitals fill before high energy molecular orbitals fill. That's Aufbau principle. You just work your way up. The greater the bond order, the stronger the bond. The greater the bond order, the shorter the bond. Okay? Alrighty, well now we got through that. Let's take a look at the